Hi, my name is Osvaldo Perez, and today I will be present our Phase A of Capstone 1 Functional Finger Prosthetic Design. I work together with my partner Jorge Figueroas and Eileen Perez. In the outline, we have the users and stakeholders, the background information, the concept of operation, the project description and objective, the project significance with the market study, the preliminary system level requirements and constraints, and finally the preliminary project planning. In the users and stakeholders, the users are patients who had their fingers partially or completely amputated, and the stakeholders are biomedical engineering student at Polytechnic University of Puerto Rico, Osvaldo Perez González, Jorge Figueroas Toro, and Eileen Perez, with collaboration of the Dr. Wilfredo Fariñas. In the background information, the amputation of the arms or hands can be caused by trauma, infection, birth deformities, and cancer. The most common reason for an amputation is poor blood flow. 77% of upper limb amputation are caused by trauma. Around 1.9 million people are living with limb loss in the United States, according with the Amputee Coalition. Only between 27% to 44% of upper limb amputees are used upper arm prosthetics. There are 6 prosthetic options for upper limb amputees and people with congenital limb difference. These are passive prosthetics, body power prosthetics, and externally powered prosthetics. Prosthetic service can be as soon as 2 weeks from surgery, depending on the length of the recovery. Ideally, you should try to begin using the prosthetics with 30 days of surgery, which allows you to adapt more quickly to using the device. For partial finger or partial thumb amputations, the different levels are distal in the phalangeal joint, proximal in the phalangeal joint, metacarpal in the phalangeal joint, and joint of any one or multiple fingers. In the concept operation, the following video represents how the different prosthetics on the market had evolved and how advanced the technology is at the moment. It also compares from the first known prosthetic, which was the toe.
A prosthesis is much more than a medical device. It also completes the wearer's sense of wholeness. It gives emotional comfort. And so the history of prosthetics is not just about the advancement of medical science. It's a story of human beings who miss an essential part of their self. It is a story of human beings struggling to regain a wholeness that they have tragically lost. The earliest known prosthetic is not a leg, arm, or even a fake eye. It's a toe, a big toe, belonging to an Egyptian noblewoman living around 3,000 years ago. Now, this may seem odd at first. A person can technically live their life with a big toe. But to Egyptian society at the time, your big toe was culturally important. To Egyptians, wearing sandals was an important tradition, important enough to warrant the construction of this early prosthetic. This big toe shows that prosthetics is as much about function as identity. For the next big revolution in prosthetics, we have to go to ancient Rome during the Second Punic Wars. General Marcus Sergius lost his right hand on the battlefield. This would generally mean you're unable to enter another battle, as you needed 2 hands to hold a sword and a shield. But he instead had an iron hand fashioned for him, so he could still hold up his shield, so he could still perform his function, so he kept his identity as a general. With his prosthetic, Marcus Sergius would continue to serve in a long military career. Iron hands, such as the one the Roman general wore, would continue to be used for thousands of years up until the late Middle Ages. Knights who lost their hand would often purchase an iron prosthetic. It can be attached to the armor or to the limb with leather straps, and were often handcrafted to fit the individual wearer. Usually knights employed the same blacksmith for their armor as for their prosthetic. And while these hands could be used to carry a shield, their main purpose was to hide the fact a person was disfigured. It was much more a personal and cultural tool rather than a practical one. It allowed the wearer to retain his identity as a knight and a warrior. But such iron prosthetics were only for the wealthy. Peasants had to do with crutches. But outside of the battlefield there was the wooden peg and a hook hand. Yes, they are real. While fiction has made them the staple of pirates, and sure, some pirate amputees probably did have them, they were actually not all that common. To attach such a peg or to attach a hook hand, you would need a professional surgeon who would know how to properly cut the limb. But surgeons were uncommon on ships, so the vast majority of pirates did not have a hook hand or peg leg. But let's consider the fact that iron hands, wooden pegs and hook hands were used for thousands of years. That they were used from the Roman Empire all the way to the end of the Middle Ages, showing just how slowly medicine progressed. Unlike amputations, see my video on that by pressing the link in the top right corner. Unlike amputations, where advancements were made incrementally, prosthetics advanced far slower. The next major advances would come from a doctor named Ambroise Paré in the 16th century. He created a hinged prosthetic hand and a leg with a locking knee joint. This allowed the wearer to bend their knee and elbow, allowing them to sit normally. If you wanted to stand up again, you could lock the knee and arm in place so it wouldn't bend anymore, allowing you to walk normally. These were invented in the 16th century, but what is shocking is that this invention is still common in modern prosthetics, even though they were invented nearly 500 years ago. Up to modern day, these prosthetics saw only small improvements. Although this is not to say that advancements were negligible. Improvements, such as a prosthetic being attached through suction, aluminium prosthetics so the wearer didn't have to drag a heavy metal leg or arm around, and the most amazing of them all, a hand which could be locked into different positions to allow the user to hold objects in their prosthetic hand, such as a fork for eating. But it would take until 1861 for the next major advancement, the hanger limb. Invented by the first amputee of the United States' Civil War, James Hanger. James's prosthetic limb was noiseless, but very similar to the ones of Ambroise Paré. What made this leg so different was its affordability. This is the first prosthetic leg which was available to tens of thousands of US soldiers who lost their leg during the Civil War. James Hanger even founded a company which produces prosthetic limbs to this day, named Hanger Incorporated. And while most medicine was up and coming and advanced the field of amputations tremendously, prosthetics did not see much improvements until finally in the 1970s. Inventor Isidro Martinez made a huge impact on the history of prosthetics when he developed a low-limb prosthesis. His prosthesis was revolutionary because it is the first which did not try to replicate the motions of the human body. Instead, his artificial limb focuses on the walking pattern and reducing friction. And this is where history meets today. The story of creating artificial limbs is far from over. Scientists today are still working on improving the lives of amputees. From controlling the artificial limb with your brain, to allowing the patient to feel with their prosthetic limb, to regrowing the limb altogether. It really does appear that amputations will no longer be a problem in the future. That people will be able to feel as though they were still whole, where a person's sense of identity is no longer impaired, a future where losing a limb will be a temporary loss, and people can keep living their life to the fullest. If you like this video, give it a thumbs up. My next video.
In the operational objective, we want to create a functional prosthesis hand made in 3D printer that help people with partial finger or partial thumb amputation to achieve the maximum level of independence.
Description: the goal of this project is to design a prosthesis for patients who have had their fingers amputated to achieve a normal grasp on objects as well as achieve a maximum level of independence. Objective: with the use of motors, get the hand to do daily tasks. These motors will work in tandem with the feedback of a lightweight rechargeable battery so that the patient can do at least 60 to 70% of the force, and that the prosthetic fingers, with the help of the motor, help 30 to 40% of the force and natural movement. Mission justification. Traditional partial hand prosthetics can be very expensive. To achieve an inexpensive partial hand prosthetic, we will use a 3D printer, motors, and batteries. The mission is to achieve a functioning myoelectric prosthesis that will allow amputees to live a fuller life at a much lower price. Project significance. Prosthesis is the medical term for artificially substituting a missing part of the body. Prosthetics is the medical science of creating artificial body parts. Only between 27 and 44% of upper limb amputees use prosthetics. Many materials can be used for prosthetics like aluminum, titanium, magnesium, copper, and steel. During this project, we will be using a 3D printer and focusing on people with partial finger amputation. We want to create a prosthetic that will work as real fingers would. As prosthetics are so expensive and many people can't afford one, we hope to achieve an inexpensive one that will allow amputees to live a fuller life and reach a new level of independence. The market size for prosthetics in 2020 was $9.22 billion. For 2028, it is expected to be $13.12 billion with a compound annual growth rate of 4.51. For upper limb prosthetics, the market size was $1,077 million in 2018. By 2025, it is expected to be $2.3 billion with a compound annual growth rate of 11%. Reasons for growth rate in the market: diabetes, technological advancements, diseases and traumatic injuries, and increasing number of accidents. According to WHO, in 1980, 180 million people had diabetes. By 2014, 422 million people had diabetes, many of these resulting in amputations. Every year in the U.S., diseases and traumatic injuries cause 185,000 amputations. 45% of the amputations are due to traumatic injuries. The market also has restraints that are mostly the high and increasing cost. The global prosthetics market is segmented based on component, technology, end user, and geography. Component can be upper limb extremity or lower limb extremity. Our prosthesis is a hand, so it will be upper limb extremity. Technology can be body powered, electrically powered, or hybrid prosthetics. Our prosthesis will be electrically powered. It will be a myoelectric prosthesis. End user can be prosthetic clinics, hospitals, and rehabilitation centers. And geography, North America, that is most of the market, Europe, Asia Pacific, and the rest of the world. To the left, you'll see prices of existing prosthetics. A cosmetic prosthetic can cost around $5,000. A functional prosthetic can cost $10,000. Myoelectric prosthetics can be between $20,000 and $100,000. And a myoelectric prosthesis of a partial hand can cost around $18,700. To the right, you'll have an estimate of the materials we will be using on our prototype. ABS filaments $50 per 50 pounds, motors between $20 and $25, fishing wires $6, and flexible nylon paracord $10. It will take about 14 hours and $100 to make these prostheses. If we charge $200 per each prosthesis and make 40 per month, we'll be having earnings of $4,000.
Here we have the preliminary system level requirements and constraints. These are our measure of effectiveness, or MOEs. We have to comply with ISO 13485-2016 that is designed to respond to the latest quality management system practices, including changes in technology and regulatory requirements and expectations. This has an emphasis on risk management and risk-based decision making, as well as changes related to the increased regulatory requirements for organizations in the supply chain. We have to comply with FDA regulation section 8903420 that regulates hands and external limbs components, mechanical or powered. With this regulation of Class 1 medical devices, we assure of good manufacturing process. Class 1 devices are exempt from pre-market notification procedures. We have to comply with UL 2054 and UL 1642 that in this case of medical devices using batteries, manufacturers can now use the proof of compliance with UL 2054 and UL 1642 as evidence of a device safety and effectiveness. We have other MOEs that are should be battery rechargeable, should be cost efficiently, must be lightweight, should be safety to the patient, will friendly design, should grab objects, should be durable, and must be biopleasant to the body. Here we have to continue with preliminary system level requirements and constraints with the measure of performance, or MOP. Should be quick recharge up to 90% in just 3 hours. The device should be battery useful for at least ensure 12 hours run, should be easy operational function activation, should hold at least 5 pounds objects, weight should be less than 5 pounds, the power source must use rechargeable batteries, material should be low cost, less than $100, materials should be high quality, it must withstand temperatures of at least 120 degrees, with manufacturing costs less than $100, with low sale cost of less than $250, to install in the arm should be less than 5 steps, the patient should be able to put it alone, should be useful for all entire useful life of the battery, at least 5 years. Here we have the quality function deployment, or QFD, or house of quality. We can see the MOEs, or the customer requirements, with their importance of each one on the left, and the MOPs above. Below, you can see the units and the targets, and the TV. And on the right, the compliance points. As you can see, the values obtained in this table show that our measure of performance meet customer requirements. Here we have the preliminary project planning. As you can see, Eileen and Jorge will be working on Subsystem 1 of Controls, and Osvaldo in Subsystem 2 of Design. We propose as preliminary date October 15 for the Phase A review. Thank you.